That's awesome. All right. So let's go ahead and let's get started. The problems that we're going to be working on are up on Canvas if you would like to follow along. They are labeled 17.45 practice because that's the end of this chapter, which means we're getting close to a what?
No.
A quiz! Ladies and gentlemen, a quiz! I love it.
No.
Going to happen on Wednesday. Yes.
Oh, that's what
What's that?
We haven't opened those.
No open note quizzes. All right. So the last topic we have to cover in 17, and remember that 17 was kind of this conglomerate of a bunch of different topics around equilibrium chemistry. The last one we have to talk about is the solubility product stuff. All right. So the first question asks us about solid silver chromate. Says it's added to water, and some of the solid is not going to dissolve. So when we talk about KSPs, a lot of what we're dealing with is slightly soluble salts, right? Things that don't completely dissociate when they hit water. In this case, we have this silver chromate, which we are given to be. If I was a truly mean teacher, I would not give you formulas, because you should already know how to write formulas from names, because we talked about that a lot in your honors chemistry classes. From there, we're told it does dissociate partially, and we're given the silver ion concentration once the solution comes to equilibrium to be 1.3 times 10 to the negative fourth. So we are given this random piece of information about what happens at equilibrium. If it is behaving like a salt, it's going to dissolve into what two parts? Good. Anybody remember the charge on one of those two things?
CrO4 negative 2.
Correct. Which makes the silver a +1. Okay? Please remember that our salts before they hit water are solids. What does that mean about equilibrium? They don't matter. Okay? We're told equilibrium of this one in particular is 1.3 times 10 to the negative fourth molar, meaning moles per liter. From here, we are asked, what is KSP? What do you want to start with? Where can you start? From all you know. We can assume, or assume, that both of these start at 0, right? That's a good one. Right? What else can we do? We can write the change. What's going to go here? Why 2? The 2 out front. You have to make sure, and this is probably where most of us will make our mistake in solubility problems, that you write the correct dissociation. If you miss a 2, then your whole calculation gets completely thrown off. All right? What happens over here? We don't know this, right? That's okay. We'll get there. We have a way of figuring it out, don't we? How do we figure it out? We're going to take that molarity we were given at equilibrium and divide it by 2. Because we know that the change from 0 up to that final molarity at equilibrium is going to be a change of 2x. So we can figure out what x is. I got a number of that. I'm going to put that in my equilibrium table in hopes that we see what we have to do next. Yes, ma'am? Yes. What's the K equation? And this is something that I would have expected us to write early on. The equilibrium expression is one thing you all know how to write. In this case, it would be products over reactants. Are there any reactants in this case? There are not. So we would write out our equilibrium expression. Y squared, because of the 2 in front. Don't forget that. All right, next thing we have to do is figure out what K actually is. So we're going to take our numbers at equilibrium. We're going to plug them in. The question asks us, what is the K value? That's it. Please remember there is a KSP. Why do we say SP? Because we're dealing with something that is slightly soluble. Can I erase? Move on to number 2. The KSP questions are usually long worded but easy solutions. All right, number 2 says the KSP for calcium fluoride is given to be 3.9 times 10 to the negative 11th. We're assuming that CaF2 dissociates. Remember that it is a solid when it starts, completely when it dissolves, and that there are no other important equilibria affecting its solubility, aka the temperature isn't being changed, we're not adding anything, etc. Our goal is, what is the solubility of CaF2 in grams per liter? All right, so when it dissolves, what does it dissolve into? So Ca and F, what are the charges? Don't forget that there are 2 of the fluorines. Okay. When they're in their ionic forms, they're aqueous. Don't forget our solids don't matter. Yeah.
Question. What we're solving for, the solubility of 6F2 or CA?
CaF2. We're going to talk about that here in a second. Okay. We know the K. We know Ca and F. What do we start with? What's the change?
Plus 2X.
Well, plus X here, plus 2X here. What's the expression going to look like?
2X squared.
Well, let's start with just the general form. From there, we have this value, and we have expressions for equilibrium. Next thing we need to figure out is what is actual X. So we're going to take our numbers, we're going to plug them in. Two x squared becomes what? 4x squared times x gives you this expression. You solve for x with a cubed exponent.
For this equation, do we divide by 4 to the cube?
Divide by 4 first.
Okay.
And then you take the cubed root, which is a button on most calculators, by the way. Yes. is correct. That is in molar, ladies and gentlemen. Yeah.
It's in math.
Mine actually just has like an actual one. No, that is not a final answer. This gives us the information about what the concentrations would be at equilibrium, right? One of the things to realize is that One of the things to realize here is that the amount of this at equilibrium is going to equal the amount of calcium at equilibrium, because this is a 1 in front of it and this is a 1 in front of it, right? So what we're saying then is that these two are going to be equal. Take the equal volumes and we get that CaF2 is going to be equal to just 1 Ca. So our molar solubility is this. We don't want our solubility in moles though. We want it in grams. Bless you. So we make the assumption that the concentration of CaF2 is equal to the concentration of Ca2 plus in this particular case, just because they both have 1s in front. Okay. Next thing we're going to do is we have to convert our molar solubility to mass. So how do we go from moles to grams? The molar mass of CaF2 when we do that, we get this guy. So that's our actual solubility in grams per liter. All right, one more concept, and that's going to use our ice tables pretty effectively. It's going to be the common ion, something we talked a little bit about in class. What happens if we add an ion that your solubility might already have in common, aka using this particular reaction, which is what we're going to use in the next one. If we started with a number other than 0, what happens? Okay, our calculation becomes a little bit more complicated, is what happens. What do you mean? It's not 0. Because we're analyzing the common ion effect.
Not keeping it 0 is easy.
I know. Common ion. All right, so we are going to use the exact same reaction. In this particular case, in part A, we're asked to calculate the molar solubility. So in other words, we don't have to do that final calculation. I think it's like NO3 too. I remember the end of the sentence. Okay? First thing says, what is the molar solubility of CaF2 if we start with some amount of calcium nitrate? Now, does this have anything to do with calcium nitrate? No. Does calcium nitrate have an ion in common with something that is going to appear? Yes, it does. It's that Ca, right? So that's going to be our starting amount on our table. From there, you've done this before. You've done this exact thing before. What do you do next? We're trying to find X at this point. What do we set up? The expression for KSP is the same one we talked about before. From there, what do? We plug numbers in. We know that KSP is 3.9 from the previous problem, times 10 to the negative 11th. We know what calcium is going to be at equilibrium. And we know what fluorine is going to be at equilibrium. And you'll remember the shortcut we talked about. What was the shortcut? Let's ignore the addition of X. That means that this whole term just becomes 0.01. What are the conditions for ignoring X? Two magnitudes of order lower than the number you're adding or subtracting from at the end. Okay? All right. Continuing to solve, what do we get for X? Please remember that 2x squared is 4x squared. Sounds about right to me. Anyone else get the same number? 3.1 times 10 to the negative 5th?
Yes.
Okay. Okay. Remember that when we solved for X in the previous problem, that's what the molar solubility was. So that's your molar solubility. That's the end of the question. All right, part B says calculate molar solubility if you add .010 molar NaF. So now, NaF, is there an Na in our equation? Absolutely not. Do we care about the sodium?
No.
We don't. Do we care about the fluorine?
Yeah.
We do. When sodium fluoride dissolves, it leaves behind an F negative. Do we have an F negative up here?
Yes.
Heck yeah, we do. So instead of starting with a number here, we start with a number there. What's our rule? We can ignore it as long as our number comes out to be small enough. Our number came out to be small enough last time, right? Times 10 to the negative 5th is a few orders of magnitude smaller than the 0.01. All right. No, I didn't erase that, but I took that. So again, it's an equilibrium problem at this point. You've done the equilibrium problems. If we ignore the 2x, what do we get x to be? Much easier to solve, right?
Really?
What'd you get?
3.9 times 10 to the negative 7.
Anybody else get that? 3.9 times 10 to the negative 7th?
Negative 50, so I don't think that's what I got right.
3.9 times 10 to the negative 7th is the right answer.
Yeah, it's, I was like, that's not, mine's not right.
I got 3.9 times 10 to the negative 7.
Okay.
don't know what happens.
So there is your equilibrium, molar solubility. Please pay attention to the term molar solubility versus solubility in grams per liter. In one of them, you have to multiply by molar mass at the end of your calculation. Always look back at your reaction. So CaF2 has a 1 in front, which means that its molarity is going to depend on a 1 equivalent from something else. And that's it. What's up?
In
You're working on the 3 underneath the ones we just did. Yes.
cross out 2x because it would just be approximately equal to e to 4.
You're working on these 3 now. They're up on campus. Have a great day.